Okay, it seems like it's 5:16. We'll get started. Thank you once again, Joey. On to you.
Cool. Thank you, Rashid, for the introduction, and thank you all for being here. So I'm Joey. I'm a fourth-year PhD student in the CS department, and my research is at the intersection of reinforcement learning and robotics. Well, today I'm presenting on behalf of the HIRO group led by Professor Alessandro Roncone, of which I'm a member. So in this presentation, I'll be giving you an overview of the research that we've been performing in our group for the past 4 years. And at any point, if you have questions, please feel free to just speak up. I can't really see the chat while I'm in the presentation mode, so yeah, just speak up. So our work is in human-robot interaction, which broadly speaking deals with the issue of integrating robots in human-populated environments. And the reason for which one may want to do that is that robots can be really helpful to people, right? They can provide support, assistance, physically, socially, or cognitively. They can perform dangerous, repetitive, or tiresome tasks. They can augment our physical or cognitive capabilities, and that's great, right? What we think is particularly interesting, though, is that this is also timely, as these objectives are being developed in parallel with broader shifts in how robotics is being researched in academia and then translated to industrial applications. Because it's important to remember that traditionally, robots have been developed to replace people, right? This is the most impactful application of robotics in society. You have big, robust, reliable industrial robots that operate, say, 364 days a year. They can move big stuff and they never break. However, in the past 20 years, we have started to hit a wall in pursuing this paradigm of full automation. And industrial robotics is beginning to not be directly correlated with increase in productivity, right? The equation has become much more complex. There are plenty of examples of big forward-looking companies that had to revert their approach to industrial automation and introduce humans back into the factory, right? You might have seen these articles about Toyota or Tesla. And the reason is simple. Well, humans are much better than robots in a variety of different tasks. If you have to do fine manipulation or if you have tasks that involve any cognitive complexity, humans are going to be better. So for this reason, we have recently moved towards a paradigm in which humans are helping robots accomplish complex tasks. Robots are still doing the same things they're doing 20 years ago, and humans augment them with the superior motor, perceptual, and cognitive capabilities. This is better for humans, and this is also better for robots. But more importantly, it helps seed this idea that humans and robots collaborating together is a clear opportunity for the field. So if robots replacing humans was the past of robotics, then people helping robots is what we can see the present of robotics. But what everybody is working towards is a future where robots are going to be helping and augmenting humans in a variety of different domains and applications, from logistics, manufacturing, construction, to assistive technologies, healthcare, and finally to the home, right? They're going to deal with untrained people who are not used to being around robots. They're going to need to perceive and predict people, and they're going to have to interact with people in a natural way. This on one side is a clear societal, economical, and technological need that we see robotics being pulled towards. And on the other hand, it's also an opportunity in terms of moving forward the state of the art in the field to make this vision of robots helping people materialize. So this is the work that we do here in the HIRO group, obviously in collaboration with other people within CU, outside of CU, and within the broader community. We have this strong objective to work towards, and we sit on top of the state of the art in robotics, machine learning, AI, and human-robot interaction, right? And we're working to get there. We believe that we're going to get there by looking at robotics and HRI as a system science, and in particular by investigating three fundamental and partially overlapping problems in the field. These three problems also constitute the research strands within our group. So I'm going to be talking about this a little bit more in the rest of the presentation. But the first is working on robots that are safe. The second is working on robots that are performing in complex environments. And the last on robots that are better teammates for people. So there are quite a number of us, PhD students, master students, undergrads, postdoc, working on these problems in a group. If you're interested in any of the things I'm going to be showing today, please visit the link, our website, and reach out to us. You can reach out to Professor Alessandro directly, or you can reach out to any of us PhD students. And finally, for reasons of time, I won't be able to show the entirety of the research we've been doing in the lab, but I hope that this is going to be a good overview. So before we look at some works in each of these strands, I'd like to introduce now a motivating example that I'll be using throughout this presentation. There's collaboration in close proximity. We can define it as an interaction in which humans are co-located in space and time and continuously share large portions of their operational space. So from here, you can pick your favorite, right? You can have recycling sorting, you can have a kitchen, maybe in an operating theater, and so on. Well, this metaphor is particularly useful and interesting for two reasons. These applications are perfect domains for robots to be useful. However, robots are also pretty bad in these environments, while humans are quite good at them. So an important question to ask is, how can we enable robots to proficiently operate in such an environment, right? So let's look at what this means for strand 1. I should have been clicking, I guess. So strand 1 is the one working in physical HRI, human-robot interaction, which is the problem of robots interacting with humans physically, being safe and operating around them, avoiding people, and so forth. And this problem of collaboration in close proximity is challenging to strand 1 for multiple reasons, right? So let's consider an example. Let's say a professional kitchen. So this is a pretty high pressure environment for humans to be in, right? Both the cognitive and physical loads are high. There are significant safety hazards in the kitchen. There are plenty of things that can harm humans. We have multiple agents, each with different things that they might want to do. And these things sometimes conflict. The dynamics and kinematic constraints are difficult. Space is at a premium. There's a lot of clutter, and you even have moving obstacles. And finally, you have collisions that inevitably occur, right? For the purposes of strand 1, this is a perceptual problem. Robots cannot perceive humans and other obstacles with the precision and speed that is needed to perform in these environments. So the traditional method of having some external vision sensor, say a camera, suffers from the limitation of occlusion, right? The robot's own body and maybe even other objects in the environment can occlude its vision system, and it doesn't have a full view of what's happening in the scene. To solve this, we can look at humans and see how they perceive the space surrounding their bodies. So one important difference is that humans can sense the environment through onboard sensing, right? And onboard sensors do not suffer from occlusions. So what do I mean by this? Onboard sensing can provide complementary information to vision. So you can integrate this with your existing vision systems. And inspired by the concept of peri-personal space in humans, we can use both proximity and touch to allow us to robustly cover the spectrum between, say, contact at arm's length and contact itself. Right. So on this topic of onboard sensors, there are some of us in the group who have developed a robotic skin for bidirectional touch-centered human-robot collaboration in close proximity. So the skin contains various sensors. There are inertial measurement units, proximity sensors, contact sensors, pressure sensors, and so on. Another direction that we have taken this in is in collision anticipation. So in close proximity human-robot collaboration, collision can be inevitable, right? Humans are very fast, and they can be very difficult to decipher. It can also be the case that the constraints in the environment make it such that avoiding collision is impossible, right? So consider this paradigm shift. Instead of insisting on safety at all costs, what if we just ensure that any contact that we have is safe? And maybe instead of avoiding collisions, maybe we can just anticipate them and act accordingly, right? So Caleb, who is a PhD student in our group, his work considers this in 4 phases. First, we can detect nearby objects. Then we avoid obstacles when it is possible to do so. If not, we ensure that the contact is safe. And finally, we recover and return to the main task with as little loss of time as possible. So proximity sensors provide information about obstacles and humans who can be obstacles. And here you can see one of our proximity sensors, and you can see how the output corresponds to the human hand that's approaching it. So there's a bunch of math that I'm not going to talk about today. Instead, what I want to do is to show you a video. So that's Caleb interacting with our robot. And with a single sensor activation, you can see that the robot is able to avoid contact. Right. And with multiple sensor activations, and yeah, the visualization on the right is the proximity readings that the robot is detecting. So you can see the green balls being the closest object. So again, I'm going to not go into this in too much detail and jump towards the post-contact behavior. So what we want from this is that if we have better whole body awareness with the robot, we can have better post-contact behavior, right? So one more video. So you can see how the robot is reacting to contact, right? It is not just avoiding contact, it is responding to it. So in summary for strand 1, and particularly in this work, so perception in close proximity grants robots new capabilities. If we can, we avoid contact. Otherwise, you can reduce the force of contact and then try to resume the task. And this really enables a paradigm shift in this space. You can have controllers that gracefully fail and so on. So now let's look at the second strand, which is focused on robotics proper. And it looks at improving the state of the art of robotics for these complex environments. Human populated environments are complex, right? So, and if we go back to this professional kitchen scenario, we can clearly see that we are way better than robots, right? Humans are better at robots in this scenario because we have better hardware. The hand is one of the most complex parts of our body and key to our evolutionary advantage. We are also better at using tools and interfacing with the environment with more than just grasping. This is in stark contrast with the state of the art of robotics, which primarily focuses on grasping or pick and place, which is a form of prehensile manipulation. But humans and animals do much more than that, right? We can push, pull, throw, catch, flip, roll objects. And all these skills fall under the umbrella of non-prehensile manipulation, basically anything but grasping. So this is a fairly underexplored area of research due to the complexity that arises from the nonlinear interactions between robots and real objects, the requirements for state sensing and dynamic control schemes. However, if we were to deploy robots in these complex environments, it would be particularly interesting because it will increase the portfolio of capabilities at the robot's disposal. So for this reason, Anush together with Ishan set off to explore this space, and they're both PhD students in the group, more specifically to investigate the hypothesis that among the various non-prehensile manipulation primitives, poking is the most fundamental and complementary to grasping. So one limitation of grasping is that it's limited by robot reach and complementary object and gripper properties, right? For what concerns the most investigated non-prehensile manipulation primitive, NPM primitive, which is pushing, we are still limited by the robot's reach, but also by the manipulation speed. On the other hand, if we're poking, poking is not limited by robot reach, right? You can poke something further away than your robot can reach itself. It allows for faster manipulation, and it does not impose strong restrictions on object properties, right? Even if your object doesn't fit within the robot gripper, that's fine. So to investigate this hypothesis, Anuj formalized poking and its control method in the following way. So we have an object at rest on a planar support surface. A contour point is chosen and extended in the normal direction away from the object. The end effector will then execute velocity control from this point to the target contour point to send the object in freestanding motion until it comes to a stop due to friction. Right. And so based on this formalization of the poking primitive, they created an RRT-based algorithm that combines this control method with sampling-based planning in an action-oriented approach, which means that we are only going to plan only the physical pokes, and all the nodes in the planning graph are achievable configurations. So these valid actions are generated in a pi-bullet-based physics engine, which is desirable since inverse modeling of frictional contact and object motion can be intractable, or they may not guarantee feasible robot motion. So the integration of valid poking specific control inputs to RRT ensures that all nodes in the planning graph are achievable configurations, right? While the algorithm ensures exploration bias with the largest coverage. And then they use a modification of the algorithm, of the RRT algorithm, that decouples skill modeling and object path planning to allow for the evaluation of multiple skill models, which can directly improve planning outcome. So the way they go about this is first they sample QRAN, a sample pose. Then the candidates for valid contour points must then lie on the other side of this randomly sampled pose, right, within the cone originating on the sampled target. Then these points are then extended in a normal direction away from the object to yield striking points. And then they compute this. They compute the relevant joint configurations for the contour and striking points. And then there's a bunch of collision checking that goes on. And then they also sample velocities for the end effector, which are then converted to robot joint velocities, right? And these actions are then applied to yield resultant poses in simulation. And the resultant pose that is closest to the sampled pose is chosen. So you repeat this over and over until the goal is reached. And the shortest path is computed as the one with the fewest number of pokes, right? And if halfway through you find that the execution is off, you can replan on the fly, right? So this planner can behave in a closed loop manner. So they evaluate the algorithm against pushing and grasping in 6 scenarios of increasing complexity, motivated by a two-robot collaboration setup. And they're in this shared workspace that's designed to demonstrate robot environment characteristics that make poking an important skill to have for robots. So for the first 3 scenarios, all 3 modes of manipulation work, right? So the reachable workspace for both robots overlap. So pushing and grasping have no issues, right? And the object fits the gripper, so grasping works. In the 4th scenario, the reachable space for both robots do overlap, but the object is too big to be grasped directly by the robot. And so pick and place fail, right? Because your robot gripper cannot pick up the object. Poking works perfectly, as does pushing. However, pushing is a bit slower than poking. So you can see both the poking and the pushing work. Yep. And then for scenario 5, they had a non-planar obstacle across the middle of the shared workspace. It's an elevated bridge kind of thing, tunnel obstacle. And as expected, poking succeeds, but pushing fails, right? Because pushing, you cannot push the obstacle all the way because there's an overhead. Sorry, you cannot push the object all the way because there's an overhead obstacle that's in the path of the pushing action. But grasping in this case works because it doesn't operate in the planar regime, and it can just lift the object directly over the tunnel. So scenario 6, we have non-overlapping workspace, and that causes both grasping and pushing to fail. But poking still works if you have impulses that are high enough to get the object across the workspace boundary. So you're basically like pushing the object really hard so that it gets across into the other robot's workspace. And then here's just some quick results. Well, poke planning is faster than pushing, and you have a higher success rate. And in some scenarios, picking and place or pushing just don't work at all, right? So in the real world, they managed to confirm the simulation findings. They do find that the task times are higher because the simulation doesn't capture sensor noise and other non-linearities that are due to contact dynamics between the robot and object, or between the object and table. And as a result, more replanning is required. So pick and place always succeeds in scenarios 1, 2, 3, and 5 because there's no uncertainty in the object pose. So manipulation basically boils down to just moving to a predefined grasp configuration and then moving to the goal location, right? But this is not the case in the real world. A fundamental difference with grasping is that sensing uncertainty leads to total failure in grasping. Whereas for poking, even if you don't have perfect sensing, you can still poke. You just have some partial failure that you have to replan for on the fly. And then lastly, after developing robots that are safe and robots that are better performing, we focus on robots that are better teammates, robots that can maximize team efficiency, and that can enable the human-robot team to be better than the sum of its parts. So in Strand 3, the challenge is that, well, humans work better together with each other than with robots, right? We are better at perceiving and predicting the behaviors of other humans, or in synchronizing and negotiating with each other than with robots, right? You can't negotiate with robots quite as easily as with other humans. Pattern recognition has been honed by millions of years of evolution, right? Our ability to recognize a face in, say, a tree or in toast is pattern recognition. And we will apply patterns even when there's no pattern, right? It's so powerful is our sense of pattern recognition. And these are examples of visual pattern recognition, but the same principle applies elsewhere. And the question we want to ask is, can making use of these pattern-like behaviors make for better robot teammates? So there's this experimental setup. The human and robot simultaneously select a block by color and shape, and they do so secretly from their partner. If the color and shape match, the team receives the reward, and the robot removes the block from the board. If the team fails to coordinate, then there's a penalty and the team tries again. So what we like about this game is the combinatoriality of it, right? You can have thousands of different boards, and for each board, you can have hundreds of different patterns. We cut it off at stacking 2 patterns for now because 3 stacked patterns results in it's just too hard to follow. And here are some examples of patterns, right? You can either pick all the yellow blocks and then pick all the blue blocks and then the red blocks. You can go from right to left and you break ties by going up to down. That's the second sequence. Or you can pick yellow circles first, then triangles, then squares, and so on for the other colors for red and then blue. And there are many of these patterns that are possible, right? And to score and rank the pattern, they created an entropy-based metric with the goal of identifying the least ambiguous pattern. So the pattern that is easy to follow if you know it and overlaps the least with the other patterns, right? So this is the metric. I'm not going to go into too much detail, but the main idea is that you want to create a strong bias towards patterns that become unique as quickly as possible, so that less frequent blocks come first. So here are the experimental conditions that they have. There's the reward maximizing policy. That's if the robot and participant were to coordinate optimally, and then they'll get the best possible score. There's a median pattern, and then there's the best behavioral pattern, right? And with the results, they basically show that with the best pattern, the teams up from all other groups, right? And also that the scores for teams where the robot selects optimally are often negative. And as for how the humans felt about this interaction, well, the teams with patterns felt that their coordination improved over time. While the teams with the best pattern, they don't agree that a human teammate would necessarily lead to a better outcome. though there are some groups that didn't feel quite the same way. And then also teams with patterns believed that the robot was more understandable and predictable. So conclusions from that was that the patterns are highly effective in improving coordination for human-robot teams, right? And the type of patterns does impact team fluency and human perceptions of robot teammates. And the participants can coordinate with the pattern robots and predict robot behavior in novel environments, even if they don't exactly know how to articulate what exactly is happening, right? So, summary, this is basically what we want to do, right? We want to work towards this goal of robots helping people. And we want to do so by investigating the fundamental problems that look at robotics as a system science. So we think it's important to focus on these directions individually, but also to look at the intersections. And this is basically our objective for the next 3 years of our research in the lab. On one hand, we'd like to expand. On the other hand, we'd like to consolidate this work. So here are some of the output and also funding that we have gotten in these various strands, and also research directions. So we want better robotic skins that we can place on the robots at higher density. There's a bunch of work in the area of robots seeking touch instead of avoiding it. There's this upcoming project where we're trying to put a robot in a chemistry lab to work together with humans. And then in strand 2, we have multimodal planning. So instead of just poking, we can poke and push and grasp, right? We have failure recovery for space exploration. What happens if our robots fail? Like if there's some part of the robot that breaks down, how can we recover from such failure? There's multi-agent and multi-objective reinforcement learning that I work on. And finally, we have language grounding for robotics, right? We want models can reason about physical events and use this to better understand language. So strand 3, there's a bunch of work we're doing in task allocation, synchronization. Human in the loop reinforcement learning is something we're very interested in. And also using robots in education. And these two are part of the NSF AI Institute for Student AI Teaming that we participate in. And then there's a bunch of grants that are relevant to this strand. And then, well, here's a chart of like the various areas we work in together with who works in them. Yeah, and you can see that they're all linked with each other because these are very related concepts, right? Advances in one area can help advances in another. So yeah, finally, this work wouldn't be possible without support from our funding agencies and without our collaborators, past, present, and future. So yeah, and so now, if there are any questions, I can take them.
Thank you, Joey. Okay, Singwook, you can go. You can unmute yourself and ask.
Yeah, thank you for presentation. I really enjoyed your presentation, and also I'm interested in the robotics. And I have a question: the general and the specific. The general question is that you're poking the scenario. There's some many material, and there's some poking. Some case can be the not expected someplace I mean any other I mean in there any case the falling from the unexpected place of doing the poking.
So the method allows for replanning. So even if the pokes the object into somewhere unexpected, they can replan and recover from this unexpected position of the object.
And then I want to find my advisor. So could you give a time for me to meet in person? I want to sending an email to you.
Sure. So you're free to come to our lab meetings.
Okay.
If you want to attend our lab meetings, just send me an email and I'll give you the details. And also just feel free to reach out to Alessandro or any of us, the PhD students in the group, right? We're always happy to talk about our research. So yeah, you can find our contact details on our website. So
Yeah.
just reach out.
Yeah, I already searching in the website, but I want to, before the contact to the professor, that I meet the PhD first. So yeah, thank you. Yeah, I will send an email to you. Thank you.
Go for it.
Hi, thank you for the presentation. I had a question related to strand 1. I guess it was mentioned that when collision is impossible to avoid, we do prefer it, but how do we know that the environment is safe to resume into the task before proceeding? Yeah, I mean, after collision, how do we know that the environment is safe to proceed?
Well, so we have these sensors, right? So the sensors can tell you whether there's something in close proximity. And after collision, you can just continue seeing if there are other things in proximity, right? Maybe the human hasn't moved out of the way yet. So you can just wait until the human moves out of the way before you resume the task. Or perhaps you can go around the human, right? Because you know where the human is. If it's possible to continue your task without colliding again, then you can try to do so. Does that make sense?
Yep.
Yeah, and then I'm sure there are intricacies that I don't even cover that Caleb will be more than happy to talk about, I'm sure. So if you have more questions, just reach out to Caleb.
Yeah, because the way I was thinking is when a collision occurs, there are multiple ways things can go wrong. So yeah. So yeah, cool. I'll reach out. Yeah. Thanks.
Hi, so I wanted to add on to the last question. So, I mean, what sort of sensors are you using? I mean, how many modalities are you taking data from, or what sort of data are you actually using to sense the environment?
Right. So the robotic skin we're using, let me pull up this slide. Here. So we have an IMU, we have proximity sensors, which just act using time of flight, contact sensors, pressure, temperature, and so on. So I'm not quite sure like whether there's a version 3, maybe there is, but yeah, these are the 2 versions that we have so far.
Okay, so you're not actually using any vision information in this case?
Right, so the vision information will be from the external cameras. So it's hard to like put cameras on the robot's skin, right? Because it's hard to parse what's happening from those cameras. So the cameras are still external, and then they work complementarily with this robotic skin that contain the sensors that we just saw.
Okay, so are you actually maybe doing any sort of prediction, right, whether a collision might occur, or are you just detecting when the collision is happening?
So they are predicting whether collisions might occur and then trying to avoid it if possible. Right, because if you recall, they have this 4-step process, right? Yeah. Any other questions?
Yeah, I was going to say the same. Hey, anyone else has any more questions for Joey? I guess not. Okay, great. Thank you, Joey, for your time and a great presentation. Very interesting work going on there. So,
thanks for coming.
Yeah, thank you so much. Good evening. Goodbye, everybody. Bye. Thank you.